Okay, so this first video for this unit is unit 11. We're just going to kind of talk about waves, and then we're really going to focus on the wave properties. Okay, so properties of a wave. So the first thing we need to know is just what is a wave, and you can kind of follow along in your notes. But the most important thing is to know is that a wave carries energy. Okay, so we've just kind of talked about all these units, right? We finished talking about all these different units, like unit 10 and 11, where we've talked about the different types of energies, like heat energy, light energy, um, sound energy. Okay, so all of those different types of energies, they have to get from one place to another somehow. And the way that they travel is through a wave. Okay, it's important to know that waves do not carry matter. So they're not actually moving particles of matter back and forth, they're just moving energy. Okay, so if you think about it, this is an example I would show in class, but since we're not there, I'll kind of draw it. If I had a bucket of water, right, and let's say I put my hand in it and kind of moved the water around, so it kind of made some waves. Okay, or maybe I shook the bucket a little bit to make some waves here in the water. Okay, if I was to drop a ball, some kind of ping pong ball, something that floats down in the water, right? What do you think would happen with the ball? Would it move to the other side of the container with the wave, or would it just bob up and down? Well, if you guessed it would just bob up and down, then you would be correct. Okay, so that ball, okay, is not going to just magically move to the other end of the tank and back, because this energy that's moving in this wave form, right? When I put my hand in there and I moved it around, I transferred some of the energy from my hand to the water. That energy is moving through the water back and forth across the bucket, but it's not actually moving the water itself. It's not going to move the ball itself, because waves don't move matter. Okay, they can't move actual things. All they are is just energy moving through a material. Okay, so maybe it helps if you want to write down like through. So from one place to another through a material, okay, or a substance. We have two different types of waves that we're going to make sure we need to know about. The first is longitudinal. Okay, so if you've ever have a slinky, if you've noticed how sometimes you can like kind of squeeze one end of the slinky, and if you let it go, you'll see how the bits of the slinky kind of go back and forth, right, from one end to the other. That's actually a longitudinal wave. Okay, there's two parts of the wave that we need to make sure we know. The first is the compression. So that's kind of this area here where you can see the wave is compressed. And then we have a rarefaction in these areas where we're not compressed, okay, where we're kind of spaced out a little bit. So make sure you know those two things. We're going to talk about wavelength in a minute, but this is a good picture. You can kind of see how wavelength is just from the middle of a compression to the middle of the next compression, right? Here's another compression right here. So the wavelength is just that distance. We measure that as like one wave, okay? Even though it looks like a bunch of waves, in this case, it's really not, because the energy is really kind of moving this side to side motion. So I have a little bit of a better picture here on the next slide. So here with these dots, we can kind of see these are the compressions right in here. And then our rarefactions are these spaced out parts. So in this case, these little particles of matter, they're actually kind of vibrating. So they will kind of spread a little bit and back and forth. They do kind of almost vibrate side to side. So you'll see as the wave moves through, they might spread out a little bit, but then they're going to kind of come back together, and then spread out a little bit and then come back together. So again, it's not really moving those air particles. It's not like it's moving it from here to here, right? That's not what it's doing. But they may kind of vibrate in place a little bit. One example The main example that we're going to kind of talk about is our sound waves. Those are longitudinal waves, okay? And then also earthquakes. Earthquakes actually are made up of two different types of waves, and longitudinal waves are the first wave that kind of comes through. That's usually like what you feel is like the vibrations under the ground, is those longitudinal waves moving across kind of under the crust. Okay. The second type of wave is a transverse wave. This is the wave that you're probably used to seeing. We have our crest up here at the top. We have our troughs down at the bottom. And again, we can measure our wavelength by going from one trough to the next, or usually this is the more common way, is from a crest to a crest. Okay, so make sure you just know what those different parts of the wave are. And here's some examples. Okay, the main example here is light, is a transverse wave, but these are also kind of the waves we're most familiar with because we can see them. We can see them on the surface of water. You can see them in a rope. If you kind of move the rope up and down, right, you can see the wave move. That's your kinetic energy and the movement of your hand, right? Your kinetic energy that's transferring through that rope. So you're moving energy, right? Energy moves in the form of a wave. That's why it moves up and down. Also, earthquakes, again, this is that second wave. So if I think about like the crust, the first wave is that longitudinal wave that just kind of moves underneath the surface. You just feel it like little vibrations. The second wave that comes through is our seismic wave. This is usually like when there's so much energy that's being moved, it'll be moved in a longitudinal way, and then it's also moved in a transverse wave. So when you start getting this transverse, it's up and down, that's when you start to see the crust, like the ground itself, actually separate. Sometimes you can even see the ripples in the ground, right? Especially sometimes after an earthquake, you can almost see like the up and down of like the pavement or the concrete, where that transverse wave moved through. Properties of a wave, we've talked about wavelength. So this is either from like a compression to a compression or a crest to a crest. Okay. Frequency is just how many waves there are every second. Okay, so per second is the key word, and we measure these in hertz. So I can determine where one wave begins and ends because I just kind of measure from the same point. So I just kind of start in the middle, and I want it to go up and down. Okay, and back to the middle. So that's one wave, 1 hertz. 2 waves, right? So there I have 2 waves, 2 hertz. Next I have 1 wave, 2 waves, 3 waves, 3 hertz. Okay. Amplitude is just the height of the wave, basically. So here we have a low amplitude, we have a low height. Here we have a high amplitude, so we have a high height. This is like, this is the main point here. More energy, more amplitude. So if you think about, 2 things that you drop into the water, which one's going to make a bigger splash, right? The object that has the most mass, right, is going to make the biggest splash because it's carrying the most energy. If I like a human, right, if you jump into the water, you're going to make a big splash. You're going to make some waves, right? Those waves are going to be higher or taller than if you just dropped a pebble into the water, right? Because you're carrying more energy than that pebble is. Okay. The last property is speed. So we can actually look at this as a mathematical formula. So one thing, here's our formula. Speed times is wavelength times frequency. Wavelength actually looks kind of like an upside down Y. It's kind of a funny little symbol. And then frequency is just the F. So if I plug this in, wavelength of 2 and a frequency of 2, right, I'm going to equal 4 as my speed. Okay, and again, it's just meters per second is our units. all of these problems are the same way, right? So I have a frequency of 4, wavelength of 1.1, sorry, 0.1 times 4. Okay, wavelength of 0.01, frequency times 2. Okay. One thing that you do want to be able to do is kind of compare wavelength and frequency. So for example, and this is, I think, the last couple little questions, we can kind of look at it. So here's a wavelength, right, from the top of my wave to the top of the next wave. Here, right, if my wavelength is really long, I have a long wavelength, right, my frequency is going to be small. So let's write it, or we'll do it right here. So the bigger my wavelength, I spelled that backwards, the smaller the frequency, okay? The fewer number of waves I'm going to be able to have in that time frame. Here, on this one, right, I have a high frequency, I have lots of waves, and I have a short wavelength, much shorter than this one over here on the left, okay? One thing we also want to be able to look at is kind of thinking, well, how does wavelength and frequency change my speed? Okay, which I can do that pretty easily. Like, think about if I increase my frequency, right? So if I make my frequency a bigger number on the right side, that just means my wavelength is multiplying by a bigger number, right? So my speed is going to be bigger also, okay? Same thing if I increase my wavelength. Okay, if I increase my wavelength, my speed is going to be bigger. Okay, so just kind of be able to look at, kind of compare different things. Okay, the last thing is categories of waves. So we've talked about the two types of waves. Now we can kind of group them into categories based on kind of how we can study them. So the first one is mechanical wave. Okay, the main thing here is that we have to have a medium, okay, or some type of material. Okay, so either like a solid, a liquid, or a gas. Okay, we have to have some type of material in order for that wave to travel. So one example is sound. Sound is a mechanical wave, okay? We're going to talk about surface, so I'm just going to cross that out. But these can be either transverse or longitudinal. Okay, so it doesn't have to be specific. The second type of wave is our electromagnetic wave. This is what we're really going to focus on for most of the unit, are these electromagnetic waves. They're always transverse, meaning they go up and down, and they can actually travel through empty space. So they don't require some type of material to travel through. Okay, so one example here is light. Light is an electromagnetic wave. Okay, so if you think about it, it makes sense, right? Because if I think about in space, so in space, right, am I going to have sound? Okay, so remember, in space, there's no material. There's no gas in space, right? Gas are like confined to the planets. That's why astronauts have to wear those masks, right? And they have to wear the breathing suits. They have to be able to breathe. They can't breathe in space. There's no air. So that means sound can't travel. So there's no sound in space either. Okay? Because there's no medium for that sound to travel through. I could talk, but no one's going to hear me because that sound basically just, it can't go anywhere. Can't go anywhere. Okay? It works in their spacesuits because there's air inside their spacesuits. So they can hear themselves. If they have like the microphones, right, that's converting those wavelengths to electrical signals, that's fine. and they can hear, you know, what's coming out of their headset because they have air inside their masks. If they were just to talk into space without their mask, you wouldn't be able to hear anything. However, there is light. That's how we get light to Earth, is because light travels from the sun. So it can travel through space just fine because it's an electromagnetic wave.